My name is Avida Zakor. I'm a faculty member in the Electrical Engineering and Computer Science Department here at UC Berkeley. And my research interests are in the general area of capturing reality, mapping, and positioning for both indoors and outdoors. The existing methods of generating indoor maps is for a person to go in with a laser pointer, shoot it to the right, left, manually up, down, and then generate a floor plan. That's extremely slow and time-consuming. And they use wheeled systems such as robots or push carts. And the issue with those is that they cannot go places where us as humans go inside the building. For example, staircases, uneven surfaces, etc. So the thought was, what if we have a human operator wear a backpack full of sensors and just walk everywhere inside the buildings that the humans can go and make a 3D map of the whole building? The data products that result from this 3D capture of the buildings is the building geometry. And from that, we can generate what's called a floor plan. This is what architects use. So the first and foremost application of the technology is in recovering the floor plan of the building in a fast, automated way.
This is our backpack system, which has a variety of sensors on it. First of which are these 3 cameras with fisheye lenses. It also has 2 laser rangefinders. This one scans horizontally, and this one scans vertically, sweeping the building geometry as he walks through. There's also this time of flight camera, which captures 3D geometry in a downward motion. The backpack also has a few atmospheric sensors, a barometer, which captures air pressure. This accurately tells us our elevation. And the backpack also has these magnetometers, these little red squares. These act as 3D compasses, and as we move through something that is heavily metallic, this changes in the magnetic field of the building, and we can capture that information. The whole system is controlled by this computer, which is run off of this stack of batteries. It can last for maybe 3 or 4 hours. The whole system weighs about 32 pounds. Nice little workout, but he can manage.
Once we're done with the walkthrough, we generate a variety of data products, all automatically. To begin with, we generate what's called a 3D point cloud that gives you the 3D geometry of the building. From there, we fit surfaces to the walls and the floors and the ceilings. And from there, we can texture map those surfaces in order to navigate inside it virtually.
One of the most interesting outputs that our backpack can produce are 3-dimensional colored point clouds. Using the laser data that the backpack collects, we can join the different laser scans to generate a feature-rich map. As the operator walks around the environment, the scans are added to the map until we have a complete map of all of the space that the operator has walked. Combining that with the camera imagery, we can generate a colorized point cloud of the environment.
The point clouds you saw have hundreds of millions of points and are visually appealing but hard to work with. The models that I generate here are very compact but still represent the same geometry. This model shows the same environment as we saw before, but is only modeled with a few hundred triangles. It also represents separate rooms in the environment and can be used for energy simulation, thermal modeling, or architectural design. This model is generated very quickly in a matter of seconds and is generated from a floor plan that we automatically produce. So this shows one of our smaller models, which is an office environment with a few rooms and a main lobby. What we've done here is taken the photography that we captured alongside of the geometry and put it on the surfaces of the model. Since this environment doesn't have any furniture modeled, furniture in the environment is plastered onto where the wall would be. But we still see where the windows are in the environment, the doors, and pictures hanging on the walls.
So what we have here is an illustration of one of the data products that the backpack is capable of producing. This is a picture of a mall. We did a walkthrough. From the walkthrough, we generate the floor plan that's shown on the upper left. I've clicked on this position, and we can see the view of the camera captured at that point. So now I can use the mouse on my screen in order to navigate back and forth and look at the different stores. And here's something interesting to annotate. And the category here is exit sign. And so if I now update, you can see that we have this label called restroom/exit. So I can continue my walkthrough and go away to visit other parts. And then when I come back, that label is still showing me the restroom and the exit.
So I've been working on this annotation tool. What it allows you to do is to annotate various parts on the image. Like here, this is a door. You can also see it in the infrared image. You can also do distance measurements. So if we wanted to measure the height of this locker, we could drag this up here, and it's close to 2 meters, so we can add that as an annotation. This allows us to make annotations in 3D space with spatial granularity so that we can mark things like heat sources, windows, make measurements on those windows so that we can figure out the area and figure out how much energy is being dissipated through them.
From there, an exciting application is to create algorithms which automatically identify and add semantic understanding onto those models. For example, laser beams tend to penetrate glass, and from there we can automatically identify where windows are. The size and locations of the windows provide information about the thermodynamics of a building. Also, we are looking to identify plug loads automatically, such as monitors and computers, and also find objects such as chairs, because these speak to the occupancy of a building and provide information with regards to its energy efficiency.
So with the backpack, you can do a quick walkthrough and collect statistics about the lights in each room, automatically locate the windows in each room, determine all the plug loads, and be able to come up with the energy model of the building in a very fast, automated way.
This is an example model which we collected using our backpack system, and it includes 2 types of images, the optical images and infrared images, such that we can observe all the objects at the appearance level so that we know what type of object we're looking at, and at the temperature level so that we know what is the temperature of that object.
For the 3D mapping, the applications are in architecture, engineering, construction, real estate, emergency response, and also for building energy efficiency applications. An important use of this backpack technology is what's called indoor positioning using images. So suppose you're in this mall and you have a rendezvous with someone at Sears, and you want to know, how do I get from where I am to Sears? So the scenario is that you take your cell phone out, you take a picture, and submit that to the server in order to find the image that comes closest. Here we go. Here's the Subaru sign. This is an image from our database, and even though this Subaru picture we took with our cell phone is much more up close than the one in the database, it recovered our position at this point in the image, and now we can know that we can walk left in order to hit Sears and find my friend. So with one fast walkthrough, we can not only generate the 3D geometry and the 3D model, but a multitude of sensor databases that can later on be used to position people inside those maps. There's 3 main exciting things about the backpack. One of them is that we've developed the first image-based positioning system that allows us to recover not only where the user is, but also which direction they're looking at. Secondly, the databases that we generate for Wi-Fi, Bluetooth, and other sensors are a lot more dense than traditional methods. Traditional methods are not very accurate. One of the hardest things about indoor navigation has to do with the fact that there is no GPS. So thirdly, because we collect so many sensors in that one walkthrough that results in the map, we can merge these different sensor databases in order to do a lot more accurate job of positioning people inside. And I think that positioning technologies that we've developed could be the base layer for all the applications that any augmented reality glass, such as the Google Glass, would allow us to do. As far as the future is concerned, I see 2 main applications. One of them has to do with the augmented reality glass. So all the things that we have today on a cell phone will be replaced with the glass. Another area that I think is important to think about is replacing this backpack full of sensors with something a lot simpler, maybe a handheld device. And the third area that I'm interested in is maybe we can entice people who occupy a building to generate the data that's needed to build these maps and sensor databases by allowing them, for example, to download an application on their cell phone. This is called crowdsourcing, and it could be a very promising area of future work. Third was that wall. Research, I always say, is like pulling a thread. You don't know what's at the other end of the thread until you've actually pulled it. And then as time goes on, you begin to see all the potential applications beyond what you had initially envisioned or imagined.